Mathematics is going to change profoundly, and in this video I wanted to capture this historic moment because in the last 2 weeks basically everything changed. Actually, everything changed already in December 2025 with the release of GPT 5.2, but couple of facts led recently a really big revolution and a lot of voices coming from mathematicians, ex-mathematicians, me included, as well as other people on a job of mathematicians, because in the sense with the recently release and solution by OpenAI of 10 mathematical problems, which were really big problems. They are not fields level kind of problems, but still they are very big problems, all of them basically being able to be published in one of the top journals definitely, and secure you a proper job if you were to be a mathematician. However, we're living in a different world where this kind of results give you something else, and also I'm going to discuss that as well. But I wanted to start in the beginning and basically tell you how mathematics is changing and what changed recently, because there was the whole wave of new results coming from AI, and this kind of new results were basically research level, well past a PhD student, because up to basically like GPT 5.4, people were talking that basically AI is at the PhD level student. You still need human in the loop to operate it, but a lot of results that came recently were done totally autonomously by people who do not have enough training, or maybe they do have a little bit of training, but they are not experts in the particular domain. And the thing that I wanted to start with is basically the Jacobian conjecture, which is a pretty well-known conjecture. Probably one of the most well-known conjectures, because this is actually something that you learned during your university courses most of the time at the higher level, during your master, for example, or early PhD, early graduate program. And this is very well known, maybe not attempted by so many people. In the end, Jacobian conjecture was false, at least in the dimension 3 and above, still unresolved for dimension 2. Basically, it was about how the Jacobian relates to the inversibility of the map. In the end, very interesting construction coming from Levent Alpouch. So he's not he's not an amateur mathematician. I think he got a PhD in mathematics. He's still affiliated with Harvard and at the same time working at Anthropic. So it's not like a total amateur, like finishing whatever studies and just doing solve Jacobian conjecture. So it's not still the level of total autonomy. You probably need some kind of interesting prompts to get it going. Later on, the result was recovered by other LLMs, but still, this was one of the biggest results. Also, you can see that by the number of views, 40 million views. I don't remember a time when a mathematical result would garner so much attention. So it was really groundbreaking in that respect. And of course, a lot of people commented on that. So that's one thing that led to a lot of other things as well. So another thing that was very interesting was coming from Dmitry. Dmitry is another PhD, but he's a PhD in machine learning. So he of course has a proper math background as well, but it's very interesting looking at his ChatGPT prompt history, because if you go over that, basically he's just giving the conjecture, giving the paper where the conjecture is discussed, and basically saying continue until the result arrives. And this kind of strategy is pretty much autonomous to some extent, because you still have to choose the problem correctly, maybe give a little bit of context on the problem, but apart from that, everything is done by an LLM. So that's very interesting. That also got a lot of views because of that, 5 million views. But this is not uncommon. This is something that I got also in my run with GPT, because altogether I managed to solve around 19 problems, a little bit more than that, but some of the claims are with other people. But basically, all of that, some of that I really needed my knowledge in number theory or combinatorics. I did my PhD in mathematics, so I also did my PhD in number theory, algebraic geometry. So Erdős problems are very close to what I did. Maybe not the closest, but still I could understand all the proofs that the machines were producing. But still, this kind of levels of results, If I were still in academia, I'm not, I'm running my own company, Ulam AI, great data if you need some for your frontier models. I'm not in academia, meaning that if I were in academia, this kind of level of problems basically get me to the, tenure track or being a professor right away, especially in such a short time. Most of the results I got here were gotten in April. I did a whole month of running through different problems, and then I played around a little bit in June, July with new models, especially GPT 5.6 when it came around in July. But apart from that, normally you don't solve this many problems in such a short period of time. And this is basically what destroys the current level of mathematics. And the final coffin to all of that, as I mentioned, was this kind of the result by OpenAI. And they basically shown that API cost through Sol was around $2,000, which is not, of course, not much, but this is, of course, not the full cost because they run the machine through a lot of more problems than that, so you probably doesn't calculate all of the costs. But anyway, some of those conjectures like non-sophic groups or constant rigidity conjecture is something that is super well known as well, even more, might be even maybe not more well known than Jacobian conjecture, but still is in the active area of research, while Jacobian conjecture was a little bit on a side. So having that, it's of course a fantastic achievement for mathematics, but now I'm coming to the point why it might be scary for mathematicians as a profession, because you have to discern the two, and I think that's what is a little bit confusing for the outsiders. There's mathematics, the ideal scenario, you prove as many theorems as possible, increase the understanding. The goal of mathematics itself is to have more theorems, more theories, more examples that will illuminate the how mathematics interplay and how it can be useful also in other domains, but for outside of mathematics, but also inside mathematics, results between like number theory, algebraic geometry, partial differential equations, and so on and so on. So there's like internal and outside goals within mathematics. But on the other hand, you have mathematicians, and mathematicians basically have the incentive structure where you have a proper career going on. You get grants, you get better university positions. Those are gotten basically from claiming better and better results. So whenever you prove a new theorem, you publish a paper, you go through a peer review, you basically go to different seminars around the world for to discuss your result, talk with other peers, other professors about your particular result. You basically explain your work. You show that you're capable of doing even more interesting work. This is how you progress in a career of mathematician. Now, usually, and this is what I'm trying to explain in my post that also got a lot of attention, is that this kind of mathematics is divided into many subdomains, and basically everyone is working in his own subdomain. You basically know of all the other people that are working in your subdomain. You can always consult experts that are working in the same subdomain but on a different problem, and also people try not to interfere with each other's works, meaning that if a particular professor is working at a problem, he's probably better than a PhD student at working at that problem. So the PhD student basically has to choose, or his advisor chooses a different problem for him to work on in order to not be, stomped to the ground by the results from that professor. But same goes to the peers, to different professors. They usually try not to have a race who solves what first, in a way. Of course, that doesn't go for super famous problems, and this is the free-for-all. Whoever gets the result first wins. But usually that works pretty well in the smaller domains. And that's why and also solving problems and solving hard problems take months to years. You can basically think about a couple of problems at a time, usually maybe one, sometimes two, three, but usually it takes a lot of time to do it because it takes a lot of mental strain and mental capabilities in order to solve a hard problem. And this is also the most enjoyable part of doing mathematics, trying to solve really hard problems. Now, this is where different problems arise with the arrival of AI, because suddenly you can have AI coming out of the blue, prompted by an amateur, and by amateur I mean someone without a PhD in mathematics, because the only definition for me for being a pre-mathematician is having a PhD in mathematics or not. So you have an amateur coming along the way, saying basically solve this conjecture, solve this problem, getting the solution, not really understanding what he's gotten, but basically he also can formalize the solution right now, or do adversarial LLM checks and check that the solution is correct with a couple of checks. And basically, the work of mathematician doesn't really make sense anymore, because if you fought for something for like a couple of months, you're trying to advance your career, and you have to think from this perspective of a job of mathematician, then basically that destroys this premise of how you get awarded credits, how you get awarded status within mathematics. Of course, this doesn't mean that mathematics get killed or get solved. I mean, we're very far away from that. Current LLMs are very good only at finding counterexamples and those kind of like very particular constructions that basically will lead you to some kind of very narrow conjectures that you can disprove, but basically they won't yet, at least yet, I believe they will in the future, they won't yet create general theories. This is where we're going with AI. But still, even at the current iteration, even if the current generation of models is the highest we go, the job of mathematician is already profoundly destroyed, because disrupted because of this phenomenon that I gave you, the example of like the mathematician is credited, the status coming from solving problems. If AI is solving the problems, then the whole system doesn't make sense. I mean, again, this only is for research mathematicians. There are also jobs in mathematics that are purely based on teaching, and those will be definitely fine. But for research mathematicians, for people who are trying to get to the top journal, top universities doing the research, it's really changing in a profound way, and we don't know how it will change in the end. So what I'm saying in the end, this is a very historic moment, because I think this is, even though the mathematics is not in any way solved, the job of mathematician is disrupted, because you suddenly have so many new papers coming along on arXiv, for example. If you see, for example, the graph for arXiv, it's right now it's basically double from where it were, I think, last year or something. Also, there's a more and more percentage of that papers being written by AI, through AI. There's some mention of Claude or codex being used for doing the job. So definitely the job of mathematician, of a researcher, is changing profoundly. And I think it's not going to slow down. So there's something to be really to really think through in academia on what you value, how the work of the researcher, how the work of a mathematician will look like, because it has to change. Because for now, if you keep the same incentive structure, then basically AI is destroying all of that, and also allowing basically everyone to compete, which might be very distressing for all of the mathematicians who basically went into the job thinking that they can slowly think about very, very hard problems and solve some of them in the time. It's a little bit like being a Go player, and and at some point you're basically trying to become a Counter-Strike Go player, which is Counter-Strike is definitely a totally different game, as you know, and this is the kind of a change, because it's not that us every mathematician will be willing to go and play around with LLMs, because that changes the nature of work completely. You were used to working with a paper and a pencil kind of a scenario, and suddenly you're forced to use computers all the time. And I totally get that not all of the mathematicians will be willing to do that. Maybe if that will be the job of a mathematician in the end, some of them will resign and use that opportunity to go and do something else, which is also fine. But definitely science, mathematics is changing, and the last 2 weeks were basically this historic moment. If you were to pinpoint that in the future, this was exactly the moment that everything changed. And I really think that is the case. We're going to see where it goes. I'm very optimistic about the future of mathematics. I'm not optimistic about academia for now, but I think the change was in the air anyway, because there was less and less budgets for science in general. If we can have LLMs doing some of the work with then researchers, and then maybe some money from the private sector is going into research, then that's going to be even more interesting. In the end, research is super important for the future of humanity, for the future of civilization. We want to have good incentives in place to have the best job possible. So I wanted to leave that comments here. You can find me on Twitter, subscribe to the channel, and see you in the next video.